discussion about it, so we can get the ideas straight, and then we can then go through the buffet of questions and actually work out what the answers are. So there are basically two regimes when we talk about time. So there's time that works with big objects, and then there's the time that I work with quantum objects. So I'm going to talk about the big objects first, because that's a bit easier, and it's a bit more. It makes a bit more sense. I mean, this doesn't make any sense at all, but it makes a bit more sense. So in the sort of 1600s, when Newton was around, he came up with the idea of how things work, and time was an absolute quantity. You could take it for a given that time moved in a line. So we have now, we have the past, and we have the future. And things progressed in a linear fashion, and if you worked out how your system worked, you could then just dial the time back, so you could just work out, put the different time into the equation, so crank the handle backwards, and you can see where the ball was going. So if you have a ball on a billiard table, and it's moving this way, with time, but if you turn the time backwards, well, you know the ball's going to go backwards. And this idea worked pretty well until we started getting into the 1800s, and they started thinking about how light worked. So, for reasons that sort of fit with the age, they decided that light needed to propagate through a material called ether. So ether would be something that would permeate everything. The entire universe is filled with this material called ether. However, because light moves so fast, it also had to be infinitely stiff. You can probably see that this sounds a bit counterintuitive. So they thought, well, if ether's everywhere, we could just work out our position relative to this ether, this thing that is stationed, just here. So as the Earth moves through the ether, all we need to do is measure our speed relative to the ether, and voila, we then can just use the ether as a coordinate system for the universe. We have this thing that is everywhere, so if you know your speed relative to that, then you know where you are. And this resulted in a huge number of people trying to work out how to do this, and it resulted in what I think is probably my most favourite scientific paper that was ever published. And so you hear about in science that nobody publishes null results. This is the most famous null result paper. They built this huge experiment on a granite slab about 1.5 meters square, floated it on a giant tank of mercury. I think they even have a picture showing like the brick construction underneath, and they span it round trying to look and see if they saw any change as the Earth moved around its orbit. So they did an experiment in the summer, the one in the autumn and one in winter, and tried to see if there was anything. And then when they came to the results, you can see on here, the dotted line is what they were expecting to see, if the theory was correct, and they ended up with a flat, what is, to all intents and purposes, a flat line. And they turned around and said, well, physics is broken. We have generally no idea how any of this is working. And it took a number of people to figure out how to get around this, and it culminated with Einstein in the early 20th century coming up with this idea of relativity. And this is how we formulate time on big scales. So this a way of thinking about how time works is to think of a light cone. So if we plot a graph of, this is distance. So this is distance you can travel, and this way is time. So now we are here. This is where we are on this plot. If we think about where we can go, so if we go in the future, time of the maximum distance we could possibly travel is the speed of light. So this is the basis of Einstein's theory. He basically decided, well, the only thing I can think about how to fix this is if we assume the speed of light is constant everywhere, and that's the maximum speed, then relativity happens. So the entire thing hinges on his assumption the speed of light is constant everywhere. So in this model, if we plot a line like that, so if we move at the speed of light, as we travel in time, this is our sort of trajectory. We're moving at the speed of light. This also works if we go the other way. So we end up with this region here in sort of time and space in which we can occupy. So we're here now, and then if we go in the future, this is all the possible physical space in the universe we could be if we were here, because we can't be out here because we'd have to travel faster than light. And the same thing happens with the past. We couldn't be here because in order to get to here we'd have to travel faster than light. So this explains where causality comes from, because if you have two events happening at the same time and they both have a light cone, at this particular time here, they don't intersect. So they can't possibly talk to each other. However, at this point here, we could theoretically have knowledge of both events. So this would be the earliest time that you can actually see both events occurring. So this is where you get people getting a bit uneasy about entanglement. So this is something you might have heard about in the news where they talk about, oh, we've got entanglement this, entanglement that. All entanglement is two particles which are enmeshed in a quantum state. So you can't describe either one independently. If you describe one, you describe the other one as well. So it's like two sides of a coin. So, well, I've got these two states. Well, one of them's heads. Well, the other one must be tails. They're described in an equation like that. And the reason why people get a bit upset about them, and this is what Einstein really hated quantum theory for, because it couldn't, at the time that it couldn't explain this, is if you have two particles, so particle A, and you have your particle B over here, they're both at the same point in time. Then if you separate them, you end up with, you could end up with particle A and B over here. What you can do is you can then perform a measurement on them. So if we now think of, this is our new now. So going from here, you have your new sort of light codes of where they could be. You end up, if you perform a measurement on one of these two particles, so you say, I want to know what you are. This one says, okay, I'm particle 1. And this one over here says, well, I'm immediately particle 2. The thing is, at this point here, their light cones are interacting. We end up with a situation of, you measure one and the other one's immediately known, even though they're too far away to be able to do anything. So you end up with faster than light communication. And this breaks things. This breaks a lot of things, and this is one of the reasons why quantum theory was ignored and divided for a long time until it started producing things like nuclear reactors, and people went, well, it must work, so why doesn't this work? And it turns out you can communicate faster than light, but you're not allowed to communicate useful information. So the information saying, okay, this one says I'm number 1, so the information going over here saying you are 2, that is information that if we intercepted it, it would be completely meaningless to us. You could think of it as encrypted or anything, but it can't be broken. It's useless information that describes this state, and we can't do anything about it. So you can do this, but you can't use it to transmit information, because you can only know what this information means if you know what that information meant. And the only way to do that would be to progress in time further until you move to this point, and you can access the information over here. So this also leads into what a wormhole is. A wormhole is where you have got a sheet of paper I can use. A wormhole is basically a tunnel between 2 points in space. So you could say go into a tunnel in Winchester or pop out in Newcastle, for example. And all that does is it just takes your space. If we think of 2D space, it's just like a way of popping through between the two places without actually having to go between all the places in the middle. You just pop through. So on this kind of diagram, a wormhole would essentially be some way of hopping from here to over here without having to do anything. As yet, I mean, this explains like the physics behind it. As yet, we don't actually know if this is something we can observe, because this is rather exotic physics, and trying to measure this anywhere near Earth is impossible. We need to see it on scales with stars and black holes. So we haven't seen anything like this, so we're not sure if it exists. I mean, the theoretical framework is there, but I mean the theoretical framework for a cup of tea reboiling itself if you leave it in the sun is there, but that doesn't happen. So this also leads on to what happens when we go to small scales. If we think of small scales, like atoms and things, rather common now that the Physics Marketing Board has got everyone to know what the Heisenberg uncertainty principle is. So it states that, in what most people understand, is you can't measure position and you can't measure momentum at the same time. So you can't know where something is and where it's going at the same time. But this is a rather special case, saying that if you can find in the quantum world 2 things you can measure, you can't measure at the same time. There happens to be a relation between energy and time. So you can't know your energy precisely and the time in which that energy exists. So if I measure a particle, how much energy do you have? I don't know exactly when it had the energy or how much it is. There's a minimum amount of error you can have in your measurement. And so that's a lower bound relative to some constant I'm going to call c for now. So what happens is, if you know your energy very precisely, so if you deliberately engineer your system so this is essentially 0, the only way that that can be a constant number is if this is essentially infinite. So that means if under very, very contrived circumstances, if you can engineer the error in your energy to be 0, so you tweak your particle you're probing with your lasers or something, you can then basically have that energy for an infinite amount of time. So you can make your particle travel and propagate through all time if you fix that to be 0. However, we can't do that, as it's not particularly useful, because this one particle propagates throughout the entire universe if that is 0. Trying to make that 0 is impossible. We physically can't do it. We don't have the technology at this point to do it. What we have been able to do is do it the other way around. So if you make this time really, really, really small, so not necessarily 0, it's really, really, really small, this blows up. So for example, you can have something interacting in a way it wouldn't ordinarily be able to do, because you suddenly make the time in which it does it really short. So you fix this. So what this fundamentally means is you can get small quantum particles to do whatever you like, because you can play around with this relation and choose which way you want to do it. Do you want to do something you couldn't do, or do you want to do something over time that you shouldn't be able to do? So a famous sort of application of this is in quantum tunneling. So a way of picturing it is, if you have a brick wall and you have a line on one side. This is not going to be a particularly good picture of a line. And you have a line over here and you have you over here. In your classical, nice, fancy world, you'd be perfectly safe that the line couldn't go over this wall. It can't jump over the top. It's far too high. In the quantum picture, the line isn't a solid object. It is described as a sort of probability. So it exists in this area. So the most likely place it will exist is here, which makes sense. However, there is a non-zero possibility at some point in time. So if you make your time error such that you can interrogate this period, this part over here, your line can spontaneously just pop out over here. So this allows you to do all sorts of strange things. So theoretically, so bear in mind that this doesn't go to 0, this keeps going on and on. There is this tiniest possibility that this could be up where Pluto is now. It could be on the other side of the universe. Briefly, it could pop out for the tiniest fraction of a second and then pop back to there. So this is another reason why Einstein didn't like quantum theory, because it allows kind of things like this to happen. You can use this kind of mechanism, can allow particles to just suddenly appear and then disappear. If you notice, that means your particle isn't here and moves to here. Your particle goes from here to here. So if we replot this again for a quantum particle, you have your particle over here, and then suddenly it can appear over here. So you can do all sorts of weird things with your particle like this. However, it's not particularly useful. We haven't been able to do anything particularly useful with it, because you end up with one small quantum particle, and then you can't interrogate and probe it, and you don't have any control over where it ends up. So again, this isn't particularly useful for anything. So if we go back to Einstein's picture of how the big world works with relativity, you end up with strange things happening. So if you assume the speed of light is a constant thing everywhere, so if I'm stood here and I measure the speed of light with, I have a machine, you put a light beam in, it measures the speed of light, and then you put it on a spaceship flying around the Earth, and you measure the speed of light, you come up with the same number. Whereas if you think about it, if I'm standing here and I'm measuring the speed of something travelling, that will have speed c, c being the speed of light, and then if I'm in a car or a jet ship which is moving, and then I also measure the speed of light, if you measured that but as somebody standing outside, you would expect that to be v plus c. So if you have this experiment inside, so you have your your laser firing a laser beam. And then if I'm here and I have my experiment, I'm firing a laser beam. If you were on board the spacecraft, you measure that, you see. If you were outside, you'd actually measure this, you see. So this Einstein's thing is basically everyone measures the same speed. So if I'm standing outside the spacecraft and I measure it, standing inside the spacecraft and I measure it, you end up with the same speed, which doesn't make sense. Because if you're measuring, if I'm stood here and I'm looking through the window, you would expect this to move faster, because it's moving, and then the spacecraft is moving, so you expect something to be moving faster. It works the other way around. So if you have two spacecraft moving towards each other, and then moving towards each other with the speed v, and you're stood here and you look at the spacecraft, you would see, if you're in a car, you would see the car coming towards you at twice the speed. If I'm moving 40 miles an hour and the other one's moving 40 miles an hour, you should see the car, you appear to be standing still and the other car would be moving towards you at 80 miles an hour. Einstein's theory says, actually, if these are close to the speed of light, then you don't start measuring that. You end up getting into the thing of, as it's close to c, you start having to account the fact that if your speed is, if this for example is 0.6 of c, you end up with combined crashing speed of 1.2 c, which isn't allowed. You have this is faster than the speed of light, so Einstein you can't do that. So you end up with this weird set of maths in relativity where your time is equal to you have your time in your spacecraft is slowed down by what is essentially something dependent on your speed v. So the only way you can make sense of the speed of light you measure in here and the speed of light an external observer would measure, which would also include the speed the spacecraft is moving, is if the speed in the spacecraft is slower. So the actual beam of light in the spacecraft would appear to an observer outside to propagate slower, but then when the speed of the spacecraft is added to it, it speeds up. So you end up with, essentially this says is, the faster you move, the slower time for you ticks by. So if you have a clock on yourself and you move around the Earth in a spaceship loads of times and come back to Earth and compare that to a clock that's set to the same time, it would be slower. So we've done this, we've done measurements in the 60s where they put atomic clocks onto planes and flew one around the world, well, thousands of times. So the US government did this because they wanted to test how GPS would work. And you end up with results kind of like this. So this is a plot showing how your orbital time, this shows you here, this red line here, shows how your time slows down based on the speed the distance you are from Earth. So this is for satellites. So a satellite, in order to orbit Earth, has a fixed speed. So as you move further away from Earth, it slows down because it's further away. It doesn't need to circulate as fast. So as you go into space, you have this negative time here. So your clock slows down. I'll explain all the other stuff in a moment later. What this essentially says is you can't travel, as far as we know, you can't travel backwards in time. But you can mess around with how time works from now onwards. So on this plot here, we can't affect what's here, but we can trash around with how this works. So the way the relativity would describe this is, if you have your 2 points, you could have a light cone like that, and then if you slow time down, all you're doing is you are compressing the light curve. So you can restrict the area in which things occur. So you can restrict the area in space-time, so this is time over here. You can restrict the area of space you can explore in a certain amount of time. However, for you, because time's slow, you would actually perceive, for the same ticking of time, you perceive this to be a shorter period of time. So if this is, say, 40 seconds outside of, for an observer standing still, if you're on a spaceship, you'd think that this would be 30 seconds, for example. So you can mess around with things like this. So this is how GPS works. The satellites, as they move around the Earth, have an ever so slight difference in the time based on the clock from the ground to the clock in the sky. And your GPS chip knows exactly where it should be if there wasn't any time change. So all it needs to do is just compare the time change between the signal it receives to the one it should have. Does that for several satellites and averages it out, and you then can work out how far you are away from each satellite. So what I'm going to do now is I think it would be good to go to a discussion, because this is some rather heavy stuff I talked about. So if people can discuss and try to get this cemented, and then we can go through the questions, which use what I've described.
Thank you. Okay. Cheers. How long are we?
15-20 minutes.
Again, get some cheese, get some coffee, get some cake, chat about
what I kind of have trouble with is that the whole thing about time, it seems that we've just made up this concept of time and then trying to fit physics around it. I mean, surely time is just a huge section of this stuff happens and this stuff happens. What if the universe already is like quantum in the sense it's completely random, and like I think particles and space and like matter are actually flying around in random places, random things, and that's what stuff is actually like. And we're trying to put this concept of it being this neat linear.
Well, all that we've done is we've essentially. The easiest thing to do is think about a water clock. We fill a tank with water and pop a bung out and mark off a thing. And all we've done is we pick a physical system and go, that does something that, from our perception, does it regular. And we would just count how many times it does it and say, okay, 10 of those is 1 second or something.
Fine, so we're kind of satisfied that that's more or less how stuff actually works, and it's not just we come up with this concept that our brain understands.
Well,
you've got to comprehend it.
What I described as that picture is special relativity, which is rather, in physics terms, that's rather simple. You're drawing straight lines on a plot. General relativity is where Einstein went, well, this works for objects that are travelling at a fixed speed. What happens if they're changing and moving and jiggling around? And you ended up with special general relativity. And he basically says that gravity distorts how this map works. So you end up with, this is where you see these pictures of space-time which are curved.
That does actually satisfy as a reasonably neat explanation of how we can reconcile things apparently happening at different times as it stretches space-time.
Yeah. All that the stretching space-time is we just make the assumption that space-time that we're in is just empty. Just think of it as an empty room. And if you start putting matter into it, it interacts with space-time. It interacts with this room and changes it. So the basic idea would be that the heavier something is, the more it squeezes it together. So you end up with a high density region of space-time.
Yeah, so like a pincushion.
Yeah, exactly. So, or you put a ball on a sheet.
Yeah.
But that's in 2 dimensions. If you have 3 dimensions, it just like sucks space-time inwards, and that concentration of space-time means that you have to go through more. If you're travelling in a line, you have to go through more of it to be able to go where you want.
I'm reasonably satisfied in it. Just kind of, it's something that's troubled me from time to time.
Well, the difficulty is it's a fourth dimension. The thing is, we're 3-dimensional beings living in the fourth dimension. We're propagating in the fourth dimension. However, we can't exactly interrogate that fourth dimension. We're basically being pushed through it. We're not actually moving at our own speed through it. All we can do is we can play around with relativity and change the way that we're being, the rate in which we're being pushed through it.
Okay, that seems reasonably okay.
Well done.
Ollie, I was watching a documentary on Stephen Hawking's time travel one. If you're travelling at the speed of light and you're in a train, there was the mind thought experiment. And if you run quicker, like if you run in the train in the direction of the speed of light, time does really weird things. We've forgotten the detail of what happens at that point.
If you're in a train travelling, well, the thing is, you can't travel at the speed of light. That's the key thing.
It's infinite energy.
So your mass, the other part of what Einstein came up with, one of the results from relativity, is your mass and energy are linked together. So essentially, your mass is proportional. Your mass is proportional to your velocity squared. So as you go faster, and not velocity squared, it's
I'm already been there.
So as your velocity approaches c, this bit approaches 0. And as that's 1 over 0, that will blows up to infinity. So your mass becomes infinite. So essentially, and as that is proportional to energy, or more precisely equals mc squared, so your mass is essentially energy. It means your energy required to move that object blows up to infinity. So only if you weigh 0 can you travel at the speed of light. So this is where they get into the thing with these neutrinos travelling. Do they have mass or do they not? Well, they don't have mass, then that means they can travel at the speed of light. However, a particle that doesn't have mass is a very strange object. The only one we know of is the photon, and that's what light is. And we already have enough problems with that. Is it a wave, is it a particle, where it appears to be both at the same time, and we pick which one for convenience. With neutrinos, they act like particles. They're very heavily like particles, and so they sidestepped the speed of light business by saying we had neutrino oscillations. That actually this neutrino changes into this type, and they go backwards and forwards depending on some constants from the equations, but they swap between the two. But if you're in the train, so if you're very close to the speed of light, so for all intents and purposes you're safe, you're 99% of the speed of light and you're running on the train. At this speed here, time will have slowed down so much on the train that if you then run, you're not in your time frame. You'll be running at your normal speed, but because time keeps slowed down, a observer watching from the outside will see a tiny little addition of your speed added to essentially the speed of light, and it wouldn't make any difference because as you're moving that fast, time inside would move really slowly. So they did this in Interstellar when they moved on to this planet which had a really high gravity, this extra black hole. And so, like, half an hour on the planet was like 5 years for an outside observer. So in this case, you can plummet through the equation that I did, and you end up with the factor of 1 minus.
Well, as in you come out of school, from A-levels and
One minus that'll be what, about 10,000 times slower if when you're on the train. So you're running at like 9 meters a second on the train, which red time is running that much slower. You're tiny extra 9 meters a second at like maybe 0.1 c. So you still won't approach speed of light. But of course, that's assuming you can get you and a train going that fast. This is the big problem. This is the problem they have with CERN, where they have these particles. For all intents and purposes, the particles run at like 5 nines times the speed of light.
That is to accelerate something that isn't light.
Well, we can travel forward through time, and as I've shown, we can manipulate how you travel forward through time. Travelling back through time is a bit more interesting. So there's no reason from any of the equations in physics we've seen that none of them seem irreversible. All the equations seem to have, there's probabilistic elements, so there's nothing saying this cannot be irreversible, except one equation, which is from thermodynamics, which is always the fun set of laws that ruins everything. Which says that entropy, this quantity S, is always increasing. So entropy is always increasing. The amount of disorder, the amount of messiness in the universe is always increasing. It's not quite messiness and disorder, but that's a useful way of thinking about it. So if you have a star, you have all your matter in one nice place, and over the lifetime of the star, all the material gets shedded away, and it just ends up spreading around the place. So you go from a nice structured object to just a mess of particles. And this is saying that it's increasing. So this delta S means the rate of change of S. So the increase in S is equal to this. This is a positive quantity, as this is temperature. This is a positive quantity, because this is change in energy. And the change in energy in this case is a positive quantity. So this delta S can only be positive, which means that the entropy is always increasing. So you can use, this is called the arrow of time equation, because it allows you to, if you have a series of photos of something, and you look at them, you can see by the increase in disorder or the increase in entropy, the progression of the system. And this is the only equation, really, we can see that sort of limits the fact that you can't go backwards in time, because it's only positive. We haven't been able to make this negative. If we can make this negative, you can have a fridge that requires negative energy. So the electric board will be paying you to cool your milk and freeze your chips and things, which, whilst nice, isn't something that I think that any scientist would be confident in agreeing with. And if you could fix this, you'd also have all these perpetual motion machines and things. So this again is an equation that has been tested to destruction, and no one has, except if you play weird quantum tricks, been able to bypass. And the quantum tricks are things like, if I borrow from here, if we go back to the energy and I think, if I borrow for a small amount of time, I can do something that I shouldn't be able to do. But ultimately, it only works with small quantum particles over almost infinitely small amounts of time. So that's the question. The first question: is time travel possible? The next one is: does gravity affect local time on Earth? And in one of these cases, very helpfully, NASA have launched a satellite to answer this question for us. Jamal and those people in NASA and managed to get a nice £1 billion satellite done. So this is a map of gravity on Earth. So the red areas are where gravity is higher, and the blue areas is where gravity is lower. And as I described with the relativity, as you go forwards through time, so as you move faster and faster, approximating the speed of light, your mass will change. So what I didn't mention was, in general relativity, is that mass affects the way that time itself propagates. So the mass and time are intrinsically linked. And the essential result is, the heavier something is, the slower the time ticks at that location. And so in these areas here, the red areas where the gravity is increased, time will tick slower. So this is the amount, this time you notice is the almost undetectable quantities, picoseconds, deviation per second. So only if you left an atomic clock in one of these locations for 1,000 years, you'd probably notice it was 1 second out. So this doesn't really affect time, but it is useful because we can use the small effect on the movement of atoms to actually measure this more accurately locally. So this is using a satellite with the gravity detector in it. If we want to measure gravity on the ground, so for example, heavier objects like liquids, you can map using a gravity detector. So if you're working for an oil pipeline company, you've got an oil pipeline somewhere and you don't want to pay to have somebody go around poking the ground to find out where it is with a stick, you can just put a gravity detector over it and map the local gravity, and you can find where your heavy oil is and in the metal pipework. So to do that, you can use a detector that relies on taking a little atom and essentially dropping it. So you have a huge tank of these atoms, you just drop one every now and then, and you measure the time it takes to fall. And so you can, by measuring the fall time, you can map the gravity, because the mass will affect the gravitational field, and that will affect the time the object takes to fall. So you can use this as a way of measuring a highly accurate gravity sensor. Will space travel make... That one, that's not a time travel question, that's a space travel question.
You liked it.
Did I?
Don't you?
Well, as I said, you can't use time travel to do space. You can't use time travel in the same thing. However, this relativistic stuff does affect how space travel works. So if you want to move so from here to Alpha Centauri, I know starts about 4 light years away. If you want to get there in 4 years, you will have to travel at the speed of light. If we travel almost at the speed of light, so we get there in say 5 years, we will have, in the process of doing that, the people on the ship won't actually be in the ship for 5 years because time will slow down. So they'll be on there for 1 or 2 years. So travelling at the speed of light can make interstellar space travel a lot easier for the occupants of the spaceship because time for them will slow down. What it does mean is if you want to travel over long distances, like millions of light years, what would be for you would be a 2-minute trip. What would be for your species, several civilizations. And so you could end up there, oh, the species we departed from has now just completely shriveled up and died. We're the only bit of our species left, which could be a bit of a bum if you've gone all the way across the universe and to find that you're the last of the species. How do you know where you're going if you're travelling through time? So this is relative to, as the Earth's moving, if I travel through time, it will just move me relative to where I'm standing, so the Earth will just disappear. This is a bit of a funny question, because as I said with the Michelson-Morley experiment, they try to use like this ether material which would be everywhere in the universe as a universal sort of coordinate system. We don't have that. That doesn't exist. Every bit of space, every empty block of space is exactly the same as the next empty block of space. So if you actually came up with a usable time travel system, you'd quite happily end up going through time and a star has moved to where I am, I'm now fried. There is literally no good way of working out where you're going to end up, because there's no absolute way of measuring things relative to the universe. There's no like map, or there's no scale bar attached to the universe. So for this country with Ordnance Survey, they have essentially a concrete marker that's fixed. I don't know quite where they put it, and that is the 0 point for the country. And every part of the country is mapped relative to that, and that is the GPS 0 point for the country. It's different to the American one. Americans use, with the GPS, they have their own coordinate system. So if you go into this country, GPS works for Americans, but not for us, because we decided to put our one in ever so slightly different place. So if you stand on Greenwich, you get a 0 point, and it's not the same as the actual line, because the American side of the 0 point is about 10 meters that way. So this is the same problem with the universe, except you're going to have stars or planets and black holes going in the way. So there's no real solution to that. You just have hope. And on the balance of probabilities, most of the universe is empty, so you'll probably end up appearing in empty space. But then you've got to work out where you are. So I think, so if you see any practical time travel, you'll probably see like there's a 1% chance that you won't actually survive the initial trip. Why can't you prove whether time travel is possible by hosting a global Welcome Time Travelers Day with the landing site in a popular place? So let's make it now. This is Welcome Time Travelers Day, and none of them have arrived. Because you could use this to accelerate our technology forward through a conversation with future beings. So this presents a bit of a problem. If we have our future being, and they have a ray gun or something, because they're from the future, and they have an idea for an amazing technology, say for example, like free electricity. We can just generate as much electricity as we like from like peanuts or something. And they come back in time and tell us our primitive early self. So this is, they tell us how to do this. So then as time progresses, you get to the future where they have these machines that take electricity from peanuts. They've always had them, so you can just take that idea. The problem is the idea doesn't come from anywhere, because we have the idea because he told us, and here's the idea because we've told him. There's no idea here. The idea just, the idea is...
Unless somebody heard about it independently in the middle of those two time periods, and then it was like invented twice.
I know, but you wouldn't independently invent it if it's already exists. Why would you invent electricity if there's already electricity?
I don't know.
The thing is,
you get duplications of inventions.
Yeah, but the problem is that the current current invention influences your thought and your pattern of thought. So for example, we would discover electrons and things. Now we do it in teaching labs. The thing is, we're looking for that because we know it exists. If you don't know it's there, you wouldn't find it. So there's no you're not creating an idea here. There's no the only way to get an idea here is after this point here, where the idea is brought back to the past. Human thought is changed. So unless if somebody outside of that is independent of that mechanism, so from over here and brings it in, Or for example, if somebody had a crazy idea and this guy says, actually that's a good idea, you should look into it, that's fine. But you can't just bring back from the future this amazing technology, it just doesn't work.
Can it just change the future you though? So if you went back and then he developed to you, the new you would be different.
Yeah, but because it's all one system, he would tell you, and then.
But can it change?
You know, but the idea doesn't. Well, if you think about it in a fairly simple thing, is if you go back in time, all you're doing is you're moving to a different time.
Yeah.
If you then go back in time again, you go back to the same time. So if you tried to do this multiple times, you'd have multiple yous in the same place arguing with each other. My idea is better than the previous person. You should listen to me. This guy, that guy's 10 cycles ago. He's talking rubbish. Actually, that idea killed everyone. Don't do that. You end up with there's a scene in Rick and Morty where they do it, and you end up with everyone in the same place.
Yeah.
And you that's the thing that will happen. You only have that point. Space and time exists only once. If we're ignoring parallel universes here, in this universe, that point only exists once. So that idea needed to traverse that point. You can't. No.
Speaking of parallel universes, it's something that's very popular with sci-fi, but I think I've heard that physicists don't particularly subscribe to it. Is that the case as far as you understand?
Well, so the idea is that you have. So in a quantum system, it exists in a array of states, so it has this probability thing. When you poke it and you ask it what it's doing, it will say, I'm this. There's a whole buffer of options, so it could be this, this, or this, or this. In the sort of conventional understanding is, it just picks one of them and says, I'm this. There's the many worlds hypothesis that says every time you do that, the one that says, I'm this, is the universe we live in. And all the other options spawn multiple parallel universes. I mean, for me, I think it's just semantics because, well, yeah, it can spawn these parallel universes which we can't interact with if we don't know exist. So it's essentially the same. All we're doing is we're living in a special case of what the more mainstream theory says.
I mean, I'm not a physicist, but to me, it's not. The reason why it'd be interesting to know is because that would imply there's quite high complexity to the universe. Like, imagine the difference between one universe and infinite universes. Like, the amount of computational complexity to two types of universe cluster we live in are completely different, and that could, say a lot about, I don't know, just how much information can actually be stored in the universe. Right?
Well, yeah, you end up with as you say, if you go back to information, you're every time a quantum system does anything, you end up with almost an infinite generation of data information.
Yeah,
and
that's crazy.
Well, yeah, it is crazy. This is why I think it's a crazy idea.
Yeah,
and that's why it's not really in.
Yeah.
That's why it's not quite in the mainstream because it leaves all these unanswered questions. You go, can we measure these probabilities? No, we can't measure.
It's also not the simplest explanation.
No, it's not. It's not the simplest explanation. And we, as a species, quite like simple explanations. That it just it does this. Can we measure anything about fancy explanation? No, then why it makes me different. So, yeah. Are there time travelers from the future amongst us today? This is a fun one. This shows how even if we had time travel, how completely useless it would be. So if we managed to invent some kind of time travel where I can travel from this spot to this spot.
Sorry.
No worries.
So if I could travel from this spot to this spot 20 years ago, without having to worry about me crashing into stuff, we can just make time travel where you see it in the movies actually work. We'd have a load of problems because throughout human history, outsiders have always been treated with suspicion. So if we go backwards in time 20 years ago, into the late 90s, we could be arrested for being various terrorists or Russians, or if we go into the Cold War, you'd almost certainly be treated like a Russian spy because you're American, but you're not quite American. What's going on with you? You don't quite understand that you must be a spy. If you go back into a bit further, you could be a German spy. You go back a bit further, you could be a witch. You go back further, you're not from our tribe, we'll just stab you with pointy sticks. So that gives you. So the past isn't particularly good. Also, we don't know the language. A lot of the stuff we do know is from written records, which aren't necessarily correct. So unless if you're going to somehow manage to recreate an entire microcosm of that period and get it into a person so they can blend in, what's the point of going backwards in time? You already know absolutely everything about that time period. So that only leaves us with the future. However, the future is, for us, from our point of view, we only know what's happened in the past. Going to the future, we're left with a huge load of unknowns. So could you imagine if you were somebody from Germany in the 1920s who was Jewish and you made a time machine that went 15 years into the future, into the Second World War? That would not be a good idea. What happens in the future is a complete unknown mystery. If you were in 2013 and you made a time machine to come to now, you go, why is Trump in charge? How did this happen? You have all these small little things. So apart from maybe moving a year ahead, and even then you're taking a big risk because a nuclear apocalypse might have happened in that period. So you don't quite know.
On a very small practical level, like where to actually land your time machine is an issue, because you could kind of take off from a field now.
It turns into a housing estate.
You turn into a housing estate, and you die because your time machine suddenly is like in the middle of a nuclear power plant when it lands.
You say time traveling to the future is like going to somewhere you don't know how bad it's going to be. So I was just wondering, is it like Brexit? It's time to travel to the future, like voting for Brexit, yes or no?
I'm not getting drawn into that discussion. That's like a whole tank of worms there. But yeah, the future is an unknown. So
Mystery box.
Yeah, so the thing you could quite happily think that area is never going to be.
You could kind of take some safeguards against this, because rather like C-3PO being assumed to be a god by the Ewoks, if you, like a Connecticut Yankee in King Arthur's court, if you rocked up to a particular century with this amazing technology and appeared to have like loads of money and started giving it out to everybody, I think I've forgotten who is it that said any sufficiently advanced technology is indistinguishable from magic. As long as you can convince the ruling classes that you would like help them win wars and get incredibly rich, you could probably do quite well until.
But then you end up with a paradox. Where does that technology come from? Because in the future, we've had. This technology's always existed.
This is the problem though, because then everyone would have that technology, and then they would probably like kill you.
We say everyone have that technology. You take a mobile phone back into the past. You've only got one. You try fabricating all the microchips in that mobile phone with Stone Age technology. It can't be done. Yeah. You go out. I've got 50% battery left, and when that goes out, this thing is essentially just a fancy shiny rock. Until then, I'm the master of the world, but that's only for the rest of the million.
And they might still think it's like a threat. I mean, like medieval people would probably attack a car as like a dragon or something.
Well, the thing is, we don't know what they would do. Our records are incomplete, so we never had. Nobody's ever sent a car into the medieval age to see how they'd react. Until we do, we don't know.
They might just laugh at you. They would neither attack it nor be interested. But it's like, who's this stupid idiot who's built this?
Well, they think that our obsession with shiny objects would be highly amusing.
Just
carrying around these shiny object magical light boxes. They wouldn't see the point. Why do you want to talk to them like this when you're sat next to them? So the whole travel thing is a bit. Tourists would be, somewhat rudely upset if they went to medieval times and ended up in a pit being poked because. And then you find actually quite valuable mobile phones for time travel. That's why we haven't got any back. Everyone had phones at medieval times. They stopped with the time travellers, and when one ran out, you went where the next one would appear.
Is it a future or past?
Well, let's try the future. I mean, it's not. It can't be that bad. Maybe only like a fortnight. Maybe only a fortnight though. You can then like watch the next couple of episodes of John Oliver or something. And you go, actually, no, I don't want that.
It would make any kind of games of chance and uncertainty completely possible. Like lotteries would be impossible.
Oh yeah, all of that would go. I mean, the Olympics would become almost impossible for us to do. That's something we have to pay for.
And like crime would be a range of things, because obviously criminals would be able to travel into the future, discover whether they'd be caught. But then you'd have the police travelling into the past to trick the criminals.
You say that though. Where does the murder come from? They're travelling in the future. If they got caught, well, they must have done the murder then. You can't do that because you can't base a decision on what happens. None of this works. It basically comes to where does the idea come from? You can't base a decision off of something you see time traveling, because then the idea doesn't exist.
What? So if you went into the future and you were arrested, you're like, well, shit, I'm going to commit that crime either way now. And there's nothing I can do about that.
So
it could be like
to completely change the direction. Plato in the Forms discussed how ideas exist on an abstract plane, but we can access like shadows of them essentially. forms. What if, like, for example, we don't know what's in a black hole, and if it's constantly sucking in information, there could be like a crap load of information in a black hole, which is why some scientists think it could be like a quantum computer. But basically, what I wonder is whether, like in that case with the crime example, when you decide not to commit the crime because you know you got caught, that reality is destroyed and replaced by a new reality. And where the idea comes from, to me, could be stored elsewhere.
Yeah, but it's not just your reality though, it's everyone's reality.
Sure.
That's the thing. But the whole idea of this idea is...
But every decision changes reality, and it's the same thing, it's just...
It does,
slightly bigger
and this
scale.
is where one of the other arguments why time travel doesn't work comes from. So instead of physics saying there's a reason why, people who do information theory say this is why time travel can't work, is you end up with this mismatch of where ideas come from, and that breaks information theory.
But if we don't know where, like, in the universe, which we don't know where the information that's sucked into a black hole goes, for example, then how can you be so sure that the information of, like, the idea to invent an electron or whatever, discover electrons or whatever, like, couldn't it exist in a different plane? I don't know. Because we don't know where ideas come from anyway, like in a psychological sense.
No, but in a purely physical sense, information is the arrangement of material.
Yeah.
So it's a unique way of assembling, like, say, Lego blocks. You make something, put them in here, that is information.
Okay.
Destroying information requires effort to pull it apart. And this is what happens about how you put all this information in, and then you get this radiation off of the black hole, and that's all. It's like you put in like a Lego house, and you just get like 2 by 2 blocks coming out. Like, where's the information gone? Which is what you're talking about. We don't know enough about that special case to be able to fully trust information theory to rubbish this argument.
Okay.
If we can solve that, then we can turn around and say, well, the ideas are essentially conserved, and so this model doesn't exist. Therefore, time travel can't exist. So this is one of the ways that people are so basically coming up with a backdoor to say time travel can't exist. Information has to be conveyed between points in a linear fashion, and you can't just make it appear.
Okay.
And then the last question is, how does a flux capacitor work? Do we all get a DeLorean in the future?
You should define what it is.
I'd also like to ask, what effect does reversing the polarity of the neutron flow have to fix
Well,
things?
this is the flux capacitor. Now, the flux capacitor is very simple. All it does is, in the DeLorean time machine, there's an excess of flux. The excess of flux destroys the machine. The flux capacitor kind of suppresses that.
Okay.
That's all it does.
Cool.
And reversing the neutron flow, I assume, means it works backwards. So it provides flux back into the machine.
Cool, got it.
What
Okay.
flux, sorry?
Flux being... Dr. Brown is a rather poor scientist. He doesn't really publish much on what he does. So all of this is based on hearsay, conjecture, and what people who've seen his experiment have actually done. And so flux in a physical term means amount of something passing through something. So, for example, we have a window, air flowing through, we have a flux of air through the window. In his case, he means energy flux, so he has energy passing through the system. Too much of that blows the system up, so that's what the flux capacitor deals with. It kind of stores it so it can go through in a more managed way, because it comes through in a big burst when you turn it on. The only problem with this sort of system is they say to have DeLoreans in the future. Well, DeLorean went bankrupt in the 80s. And they don't make cars anymore.
They've tried to bring them back.
Well, there's an American company that basically went and bought the entirety of the DeLorean Motor Company wholesale and moved it to America, but they're not producing cars at the moment, they produce spare parts. So there's a potential that we'd have a really rubbish stainless steel car in the future again, that have really impractical gull-wing doors that you can't open in the car park.
The other thing annoyingly, the speed limit is a little bit too slow to do 88 miles an hour on the motorway.
Well, speed limit, but if you've been on a motorway, you can do 88 miles an hour.
So you'd have to like time travel to escape the police every move.
Well, this would be the thing. Imagine if you were time traveling and had a machine that needed to go 88 miles an hour. If you did that on the motorways in the 60s when you could go 88, and then suddenly they bring the speed limit to 70, and you're in the future and like, I can't go back. I can't make this car go fast. And you then suddenly have to go to Germany and try to travel back from Germany because you can take it up to 88 now. This is a problem. You end up with these weird regulations that come and bite you in the arse when you try to travel back in time. Or if you end up doing like they did in the third film, you go back and you go, we can't go 88 miles an hour. We have to stop at the front of the train that we've like teed up a bit. So that's all the questions that I've got from Jamal. So
Anyone else have any questions?
anyone else?
Yeah.
The travel from the person to the past, seeing themselves, would also mean that matter is transferred into a location from A to B, B being the past.
Yeah.
It's quite odd if then the person from the future commits a crime and comes back to the future. If someone actually was jailed, that would be the poor guy, the younger one who hasn't actually committed the crime.
But then it would have been later on in time he would have become this person that committed the crime. So all he's actually done is he's just served this extra part of his jail sentence.
Yeah, but it's still the duality of that person's existence, because that person would, that younger person would be in jail if you actually assume that you would be able to come back to the same stream of time. So
in this
somehow it would have created.
So in this picture, I basically said that the passage the person takes is linear. So it's the same person all the way through. The problem is with crimes, it's not just you have to be. It's the state of mind required to commit the crime, and that only existed in this person and not this person. So you end up with the weird duality. Yeah, as you say, you end up with you're jailing not the person with the mentality to commit the crime, which is something that I think our legal system is probably ill prepared with. And I don't think there's any good way of solving it, because unless if there's some detectable difference between these two people, so they have material that doesn't exist, but then how do we know what material that doesn't exist looks like? Because again, the material, we then know that this nano material exists, and it then develops science. So that's why I think that we shouldn't dwell too much on the philosophical aspect, because I think that if you look at that, the more you probe it, the more it falls apart.
Yeah, but in the moment you leave in the future, up to that point, up to the day before, you're still existent if that possible to travel back in time. So if you travel back in time at that day before you left, you wouldn't or up to the point that you actually leave, you would be existent, and then you would disappear from that time frame, so to speak. So it's quite odd how that's supposed to happen.
Yeah, I mean, we did the actual mechanism of how it happens, nobody has any idea. We don't know if it's possible yet, alone how to actually do it. I mean, it would be strange though if you have a person, if you look at a person's life on a timeline, they existed in this region here, then they went back, lived this region again, and then decided, actually, I'll go up here, and then, I'll go back and I'll, live this bit here, and then I'll then come back and live this bit here. You end up with, if you then collapse it down, the person has existed in, rather bizarre periods of time, except the periods where you end up with two of them for some point. But to an external observer, you'd see a person do this. But the other thing is, if you're trying to live a normal linear lifetime, and you do a lot of travel in the past, so you live here, and then you discover your time machine, you go back to here, you go to here, then you come back to the present, and you go back to the past over here, then you come back to the present, you live here, and then you die. You've lived that much of your life compared to, say, your family, or your brother, or your significant other, and they then live this much. So you also end up doing the thing of you end up kind of like compressing your adult life from the frame of a person who doesn't time travel. So you end up living this marvellous life going backwards and forwards, and then your loved one ends up with this deficit of you free time because you've ended up using all your life up travelling through time.
Do you have a question as well?
Yeah. Maybe it's kind of like teleportation, where you're just cloning yourself. So you got the original and then you got a copy.
Yeah.
So then when you're going back in time, all you've done is sent another copy of yourself there.
Yeah. And then when they come back, you then interrogate.
So there's loads of you, sort of.
Yeah. But then you end up with this situation of you end up with all these clones of yourself which have exactly the same value system. Would you really want to kill them after you've used them? Or you just create a copy and like, I'm going to be here, I'm going to be the boring one who lives through this, and then you're going to be a psycho, you're going to go off through time, do all these things. If you die, I don't care.
Yeah. But is there a problem, like, if you've done a murder, does the court, which clone do they accuse of doing it?
Do they jail all of them because they were all from the same person, and the person made the clone who then committed the crime? you end up with these problems of where in the dependency tree do you apportion the blame?
Yeah.
So is it from this? They had this incident and then caused them to commit the crime.
I think this is why sci-fi protagonists are often just assholes. Like, just come across as irresponsible.
This is why a lot of sci-fi just glosses over all of this problem. Just, we casually do time travel when they don't think of all the problems with it.
Cool, thank you so much. You can stick around a little longer if people have questions. Excellent. Yeah, so Ollie will be here for, all the rest of us will all be here for like half an hour or so. If anyone wants to stick around, chill out a bit, chat to each other, that's great. I just want to formally close the event now. Thanks so much, Ollie. You did really well. So yeah, this was Time Travel.